Well, today we have Corrine Yap talking to us from Rutgers University about multicolored hypergraph Ramsey numbers. Take it away.
Thanks so much, Abigail, for inviting me, and thanks to the other seminar organizers for having me. So today I'm going to talk about some work that we've done recently. This is joint with Quentin Dubroff, who's another graduate student at Rutgers, António Girão, who's a postdoc at Oxford, and Eoin Hurley, who's a graduate student at Heidelberg University. So let me start from the very beginning, just to make sure that we're all on the same page about notation and definitions and everything. So I'll be focusing on K-uniform hypergraphs today, which you probably know is just a set of vertices, V, and we have our hyperedges, which are collections of subsets of any size of V, and the K-uniform condition requires that each of those subsets actually has size exactly K. So a two-uniform hypergraph is just a graph, which we all know and love. And the complete K-uniform hypergraph will be have edge set the collection of all possible subsets of size K. And I'm going to use this notation K sub n superscript K to refer to that. And I realize that the screen up here is frozen, but I think that you can still see me through the Zoom talking to you. So I hope that's okay. So there's just this lag with the iPad. And the sort of classical Ramsey number in this context, I'll denote R sub K of T. And this is the K uniform Ramsey number. And it's the minimum number of vertices n, so that if we take any two coloring of the edges of our complete K uniform hypergraph, we must have a monochromatic clique of size T in it. So one example, oh, what happened? Somehow I swiped and it stopped sharing my screen. So let me try one more time. Okay. I think we should be back in a second. Okay. So here's maybe the first example about Ramsey numbers that you learn in an intro combinatorics or graph theory class. This value R sub 2 of 3 is equal to 6. And I want to just discuss this a little bit because there's this dichotomy between proving upper bounds and lower bounds for Ramsey numbers. So on the left side, this is actually a complete proof for the lower bound of this Ramsey number R sub 2 of 3. This is a proof that R sub 2 of 3 is bigger than 5. Because for lower bounds, what you want to do is construct or show that there exists two coloring of K5 with no monochromatic K3, which is a triangle. So here I have, I've given you an example of a coloring where a two coloring of the edges of K5 with no monochromatic triangles in it. On the right side, this is not a proof. And all of my combinatorics students are always confused on this point, but I think we're all maybe familiar with this. This is exhibiting a construction is not a proof for upper bounds, but you can show that R sub 2 of 3 is less than or equal to 6. And what you want to do there is show that for any arbitrary two coloring of K6, you must have a monochromatic triangle. So prove for every two coloring of K6, there exists a monochromatic triangle. So we're going to be talking about both lower and upper bounds for Ramsey numbers today. Most of the time is going to be spent on lower bounds, but I will include some discussion about upper bounds at some point. Okay. So now let's look into the K-uniform hypergraph case. What are the open questions there? A central open question is just looking at what happens when K is bumped up slightly from 2 to 3. What is the asymptotic behavior of R sub 3 of T? And it's a classical result from Erdős-Hajnal and Rado in 1964 that the behavior of this Ramsey number lies between an exponential and a double exponential in T, the size of the clique that you're looking for. And this is basically the state of the art. We don't really know anything more specific than, what's in this gap between exponential and double exponential. And a lot of, work has been done to try and close this gap. And a lot of people are really interested in what the truth is for k equals 3. And it actually is really important. It's not just because it's sort of annoying that this is one open case. In fact, the state of k uniform Ramsey numbers for all higher uniformities sort of rests on the shoulders of k equals 3. And that is because of this, this result called the stepping up lemma, which was done by Erdős and Hajnal in 1972, which essentially says that if we have lower bounds for k uniform Ramsey numbers, we can use them to produce lower bounds for k plus 1 uniform Ramsey numbers. And I'll go into a lot more detail about what this construction involves, but the main idea is that you take a coloring of a k uniform hypergraph with no monochromatic clique of size t, and you step up to a coloring of a particular k plus 1 uniform hypergraph, or sorry, on a particular number of vertices. And you produce a very specific coloring using the k uniform coloring that also you can prove does not have a monochromatic clique, now of size slightly bigger than t. So this is important because if we just apply the stepping up lemma repeatedly to this lower bound that we have for the k equals 3 case, we actually get lower bounds for k uniform Ramsey numbers, which are given by towers of height k minus 1, where I define the tower function here. The t sub 1 of x is x, and then t sub I is defined recursively as 2 to the t sub I minus 1. And also Erdős, Hajnal, and Rado showed that we can find an upper bound for the k uniform Ramsey number given by a tower of height k. So actually for every higher uniformity, we do have this gap that consists of a tower of height 1. And showing that R3, showing the behavior, and in particular, showing that this upper bound for R3 is correct, would then close the gap for all higher uniformity Ramsey numbers. So everything for higher uniformities really could hinge on just what's happening in the k equals 3 case. So this, but this remains open. I'm not about to tell you that we have solved this problem. This gap still remains. But there are different avenues you could take to try and figure out what's going on with R3. And one way is just to look at the definition of our Ramsey numbers and try and generalize different aspects of the definition so that you can maybe prove more general results that would have implications for R3 of t. And in particular, one approach might be just to find out what happens when we use more than 2 colors. That's sort of a natural thing to consider, and why restrict ourselves to 2 coloring the edges. We could consider 4 coloring or 5 coloring the edges. So I'm going to introduce this new notation, and just as a warning, I will be introducing sort of more and more complicated notation for Ramsey numbers. And as they get more complicated, you will have to pay less and less attention to them. I'll just tell you right now, I'll try and remind you every time it comes up of what the actual meaning of the notation is. So don't worry about remembering all the parameters. So this Ramsey number, it's again the minimum number of vertices n, but now we allow we're looking at Q colorings of the edges of our complete K uniform hypergraph, and we're looking for a monochromatic clique of size t inside. And this has been explored a lot. So Erdős and Hajnal in the same year, 1972, actually showed that if you bump up from just 2 colors to 4 colors, you do get this double exponential lower bound that we wanted to prove in the 2 color case. And many, many years later, Conlon, Fox, and Sudakov actually showed in the intermediate case for 3 colors that we do get a super exponential behavior for this Ramsey number. And Erdős conjectured that the double exponential lower bound should actually be the correct one for 2 colors. And this conjecture is open, but one way you might interpret this conjecture is that the number of colors really shouldn't matter when we're considering the asymptotic behavior of our Ramsey numbers. Whether you use 2 colors or 4 colors or Q colors, ultimately the behavior of this Ramsey number is basically the same. So that's sort of one way you could read into Erdős's conjecture. But okay, how can we tackle this idea? How can we determine whether this way of thinking is correct, whether increasing the number of colors has any effect on our Ramsey numbers? Well, one approach you might take is, why look at cliques? Why only look for clique structures in our hypergraphs? Maybe we can, pick a different family of hypergraphs and consider Q colorings where we look for monochromatic copies of other graphs. And so that, brings to light another little bit of notation where I'm replacing the T here with a G. And now for my Ramsey number, instead of looking for monochromatic cliques, I'm looking for monochromatic copies of my favorite hypergraph G. And so a question this brings up is, can we find a hypergraph where the 2-color number is different from the 4-color? Or can we prove that for most other hypergraphs, the 2-color and the 4-color Ramsey numbers are not that different? That might lend some credibility to what Erdős's thinking was for cliques. So a very surprising result from Conlon, Fox, and Rödl only 5 years ago was that actually there is a family of K-uniform hypergraphs where the Ramsey number displays a really strong sensitivity to the number of colors that you use. In fact, the 2-color Ramsey number for this family of hedgehogs is bounded above by a polynomial in the size of the graph. But the 4-color Ramsey number is at least a double exponential. And I'm going to tell you a bit about this family and tell you what these hedgehogs are. But they brought up in their paper this question of, can we do any worse? Can this gap be sort of arbitrarily terrible? Can you find a family of hypergraphs where you have a 2-color Ramsey number and you can find a big enough Q so that the Q-color Ramsey number, the difference between those is an arbitrarily large tower? And our answer to that is yes, you can actually find these graphs where you have this gigantic difference between using 2 colors and using Q colors. So this is the main result that I'm going to talk about today. We have this construction called the balanced hedgehog, so very much inspired by the hedgehog construction by Conlon, Fox, and Rödl. And what we show is that the 2-color Ramsey number for this balanced hedgehog is again bounded above by a polynomial in the size. But there is some large Q so that the Q-color Ramsey number is at least a tower of height, okay, not of height K or 2K, the uniformity, but of height log K. And I'll say a little bit about why we can only get this log K lower bound instead of something that's linear in K, for instance. So this is the main result that I want to talk about, that you can get these sort of arbitrarily large gaps. And now let me take a moment to tell you about what these hypergraphs are and what the hedgehog construction actually is. So for Conlon, Fox, and Rödl, they had this hedgehog where you take a body, what they called a body of size T, and they mainly defined it for the 3 uniform case, but you can do it for general K uniform, where you take every K minus 1 subset inside the body. So for them, this was just every pair of vertices, and you add a unique vertex outside the body and use that to complete the edge. And you added a distinct vertex for every K minus 1 subset you find in the body. So if you sort of draw out what this picture looks like, you can say these edges look like spines. And so this is what prompted the hedgehog name for it. For us, what we defined as the balanced hedgehog is maybe what you might naturally think of when I say balanced hedgehog, now that you have seen this hedgehog construction, is that we just take subsets of size k over 2 in the body, and we add a unique subset of size k over 2 outside. So these are disjoint subsets. For every spine, we add a disjoint subset of k over 2 outside of the body. And we sort of take, floors and ceilings appropriately when we have k being odd. So again, this is a body of T vertices. And for some of our results, for like various lemmas that go into this theorem, we can actually prove them for more general constructions, which is something we call the generalized hedgehog. There's another parameter S, and that tells you, you take subsets of size S in the body and add a disjoint sets of size K minus S on the outside. But I'm not going to be spending too much time on that because, it's basically the same ideas as the hedgehog. Okay, so that's the construction, and this is, the sort of weird family of hypergraphs that has the strong sensitivity to colors. So before I go on, I want to spend the rest of the time really talking about the proof ideas. Some of the proofs are very inspired by the Conlon Fox-Rödl paper, and I'll also say a little bit, some amount of sort of the new ideas that we bring to this construction. But before I do, are there any questions about the history or the statement of the theorem or any of the definitions so far? Also, since I'm connected on both my iPad and computer, I can see the chat. So if you have any questions in the chat, if you have any questions, feel free to type them in the chat and I'll see them. All right. Also, of course, feel free to interrupt me if I don't specifically ask for questions. Feel free to unmute.
Maybe just one quick clarification. So T is the number of vertices in the body, but also the total number of vertices of these hypergraphs is some polynomial in T. Right?
Yes, exactly. Yeah.
Okay, thanks.
All right. If there are no more questions, let me talk about some proofs. So let me first address the upper bound, showing that for two colors, we have a polynomial upper bound in the Ramsey number. And remember that upper bounds mean we want to show that every two coloring of the 2k+1 uniform hypergraph on this many vertices must contain a monochromatic hedgehog. And I'll just say that the reason that these are stated in 2k+1 uniformities rather than k uniformities is just for notational purposes, so I didn't have to write k over 2 floor or ceiling or whatever here. So the upper bound, I'm not going to go into too many details of this because the proof is pretty similar to what happens in Conlon, Fox, and Rödl for their polynomial upper bound. And it's also a pretty standard technique in Ramsey theory to take your arbitrary coloring and pass to some auxiliary coloring, and then use properties of that auxiliary coloring to greedily embed your monochromatic structure. And that's essentially what we do. But maybe I'll draw a little picture. So we have our coloring on the 2k+1 sets, and we have a coloring that's given. So we have, move this over here. We have some amount of pink and blue, 2k+1 sets in here. And what we do is we pass to a coloring of the k+1 sets. And the way we do that is we color something red if it has small red degree under chi. So chi prime of E is red if the red chi degree is small. And similarly for blue. And we sort of define small in a way that works well numerically with all of these things. And so for how we define small, this chi prime is actually a partial coloring, not a full coloring, in that an edge might not, a k+1 set might not have small red or blue degree, but it certainly can't have both small red degree and small blue degree by how we define small, because it wouldn't be contained in enough 2k+1 sets. So this chi prime is a partial coloring. And then we pass to a coloring of the vertices. And again, we do the same thing. We say that a vertex is red if it's red, chi prime degree is small, and blue if it's blue, chi prime degree is small. And here we actually get a full coloring. So what we do is we have this subset of red vertices, and we have the subset of blue vertices, and one of them is bigger. So we take the bigger set. And what happens when we pass back from this large red set to the chi prime coloring? Well, they were all colored red because their red degrees were small. And so that means we can find this set in the middle graph where we have mostly blue edges. And maybe we have some red edges sprinkled throughout, but it's mostly blue. So we can greedily find a subset of these where we have all blue edges. And then what happens when we pass back to our original coloring? Actually, let me do this. Then, because blue in our middle coloring meant that the red original degree was small, we have this large subset where we can greedily embed the red spines because of how we defined our middle coloring. So that is the main sort of overarching idea of what goes into the proof of the upper bound. But it's very similar to what you see in the Conlon Fox-Rödl paper for just hedgehogs. But are there any questions about this idea? Okay, let me spend most of the time talking about the lower bounds, since I think that's a little bit more interesting. So here, when we want to show this tower lower bound, what do we want to do? We want to construct a Q coloring of the 2k+1 sets on this many vertices with no monochromatic hedgehog in it. And the main idea here is that we can interpret no monochromatic hedgehog as the same thing as every hedgehog spans at least 2 colors. And I'm going to take this condition and relax it a little bit and say, okay, let's consider colorings where my new condition, instead of my condition being monochromatic, my condition is spanning few colors. And what can I do with that sort of Ramsey quantity? So our idea will be to pass from colorings where hedgehogs span 2 colors to colorings where cliques span many colors. Because I know, sort of using ideas for clique Ramsey numbers, it's easier for me to sort of use classical ideas with cliques Ramsey numbers more so than with the Ramsey number of this hedgehog. And then I'm going to apply some stepping up results just for cliques. So let me formalize this idea of passing from hedgehog colorings to clique colorings with this new definition and lemma. So you definitely don't need to remember what this Ramsey number is. I'm going to forget about it for a moment in a second. But the idea here is that now we're looking at colorings where instead of looking for monochromatic copies of G, we're looking for copies of G spanning fewer than P colors. So I have this new parameter P. And our key lemma is that we can take the Ramsey number for hedgehogs that we cared about before, and we can give a lower bound using Ramsey numbers for cliques. And so the main idea here is we start with this many vertices. So let's say that this is equal to capital N. Then we take an arbitrary coloring, Q coloring, of k+1. And what does that mean when for our definition of n, that means that every clique of size t spans fewer than p+1 colors. So every k plus 1 spans at most p colors by the definition of this Ramsey number. And then what we do is we produce a coloring, let's say a Q prime coloring with no monochromatic, sorry, my screen is changing size, monochromatic HT inside. So we start where we know with a coloring where every clique spans few colors, and we use that coloring to define a new coloring that doesn't have any monochromatic hedgehogs. And I'll say a little bit later on about, like, these parameters seem a little bit weird that we're letting p equals 2k plus 1 choose k plus 1, q prime equals q choose p, and then we have this result. Ultimately, the way that we produce this coloring that has no monochromatic hedgehogs is just by coloring sets using the union of subsets inside them, coloring every 2k plus 1 set with literally the set that is the union of the k plus 1 sets. And so that's sort of where these binomial coefficients come from. And we show that under this coloring, we don't get monochromatic balanced hedgehogs. So I'll bring this up a little later, but in terms of potentially improving the results that we get in this tower lower bound, this lemma might be a first place to look, just because we're producing a very specific coloring to show this lower bound. And maybe there's a better way to color a hedgehog. Like, who knows, we just sort of went with a coloring that seemed natural to us given this setup. But there could be a better way to do it. But I'm not gonna go into too many more details about this lemma. Instead, I want to shift focus to proving lower bounds for this, because now that we've passed from hedgehogs to cliques, we can focus on just proving lower bounds for clique Ramsey numbers, which is pretty similar to sort of more classical things that have been done. So let me now shift focus to cliques and forget about hedgehogs. I think I just have this extra slide for some reason. So how do we show lower bounds in this clique Ramsey number? One very common way to do this is via the stepping up construction. So I want to spend the next chunk of time going through what is stepping up. So if you've seen stepping up before and you understand the arguments, then the next few slides are not going to be super interesting for you. But if you haven't, I want to make sure that, you know, by the end of the talk, if you remember anything, maybe you remember how to step up from 2 to 3 uniform hypergraphs. So what's the main idea with stepping up? So we have some hypergraph. Let's say that we have a K uniform hypergraph, G, on some set of vertices and edges. And let's index our vertices by the numbers 1 through m. And we are given some nice coloring. Let's just stick with 2 colorings for now, where we don't have any monochromatic clique inside. So we are given a 2 coloring, chi, with no monochromatic KT, let's say. And what we do is we step up to a coloring of a K plus 1 uniform hypergraph. And now I'm going to call this G prime, where our vertices are now indexed by binary strings of length m. And our edges are, you know, the collection of all K plus 1 sets. And we want to define a 2 coloring chi prime with no monochromatic k, let's say 2t or something linear in t, 2t minus 1 or something. And so the way we're going to do that is this sort of choice to identify our vertices with binary strings of length m is going to play an important role in constructing this new coloring. So we're going to define our chi prime based on chi and using this relationship between the two vertex sets. So let me give a little bit more details on explicitly what this new coloring is. So let's just think, very basic 2 to 3 uniform. So we're stepping up from a graph to a 3 uniform hypergraph. So our edges in our 3 uniform case will just be strings, binary strings of length. Our edges will be, our vertices will be binary strings of length m, but our edges will all have just 3 strings in them. And what we do is we define this function that takes pairs of vertices in the 3 uniform graph and maps them to a vertex in the 2 graph. So this delta function, we define it as the maximum coordinate where the 2 strings differ. And so if you want a graphical representation of this, one nice way that I like to think about it is if you take a binary tree and you use your strings to label the leaves. So say I have a binary tree and I have U here, and maybe I have V here, then delta of UV is going to be half of the unique path between U and V. And so one important thing to remember is that this is some integer in 1 through m. And so in particular, I can also use delta to order my vertices. So if ui, where I is the delta value, is equal to 0 and vi is equal to 1, then I say that u is smaller than v. And so for every edge in my 3 uniform hypergraph, I can index them so that they are ordered according to this delta function. And then for each edge, I can produce a unique delta sequence by just taking delta of the consecutive pairs. And the important thing here is that this delta sequence is actually an edge in the 2 graph. So this is an edge in the 2 graph, which is the thing that we're stepping up from. So I have not only this way of mapping vertices to vertices, I have this way, this well-defined way of mapping edges in the 3 uniform case back to edges in the 2 uniform case. And so of course I'm going to use that to define my coloring. And I use 2 pieces of information from the delta sequence. So I take my edge and I look at the delta sequence. I look at the color of the delta sequence back in the 2 graph. And I look at the pattern of the delta sequence. And each of these possible combinations is going to define my color class. And this will make it really easy to show that if we have a monochromatic clique under this coloring, then in fact, we must have had a monochromatic clique under the original coloring chi, which is a contradiction because we assumed chi didn't have any monochromatic cliques of size t in it. Okay, so let's go through that argument. Suppose that we have a monochromatic clique, let's say in this color. And so let's say that monochromatic clique is just the vertices V1 through Vt, and they're all in this color. So I've copied over the definitions here. So what does that mean? That means that first of all, my delta sequence is increasing, strictly increasing, because of how I defined C1. And for any pair of delta values that I get from these vertices, then chi of that pair must have been red. So of course, if we just consider the edges formed by 3 consecutive vertices, right, then their delta values are going to be delta 1, delta 2, delta 3, and so on up to delta, let's say, t minus 2, t minus 1. And if I just look at the consecutive pairs, right, oh, what just happened? I think I accidentally took a screenshot. I'm not sure how that happened. I guess I don't know how to work my iPad even after having it for so many years. What buttons do what? Sorry for that. So if we consider consecutive triples, then we know that the delta value of vi plus 1 is delta I, and the delta value of vi plus 1, vi plus 2 is delta I plus 1. And so we get that each of these edges must be red. But we don't know about the last one, and we don't know about what's happening in here. Are these all red? And so here's where we require a property of the delta function, which is that if we take any pair of vertices, where I plus 1 just has to be smaller than j plus 1, and we take delta of those 2 vertices, then this is the same as delta j, which is delta of vj plus 1. And this follows from sort of a unique maximum property of the delta sequence, in that if you take delta of 2 vectors or 2 vertices, then that is going to be equal to the maximum consecutive delta value within that interval. And that maximum happens to be the same as delta j. And so using this property of the delta function, which if you don't believe me, then you can sit down and it's a pretty short exercise to prove this. We actually get that all of the sort of other edges that are defined by the set of t minus 1 vertices also have to be red. So we do get that this is a red clique. But again, as I said, we assume that we started with a chi with no red cliques of size t. I just produced for you a red clique of size t, or sorry, t minus 1. I'm off by 1 a little bit, but this is a contradiction. So next I want to talk about making this idea more general, and in particular, how the broad strokes of how it applies to our particular problem, which was a problem about spanning few colors. But before I do, are there any questions about just sort of the basic idea with stepping up? All right. So now let me talk about stepping up in slightly more complex contexts. So we can, of course, just repeat the same idea sort of verbatim for higher uniformities. So one thing to notice is that I started with 2 colors in chi, and I increased the number of colors up to 4 colors. And so you can keep doing this by considering in your new coloring, considering every possible combination of colors of the delta sequence, and also patterns of the delta sequence, where by pattern I mean like in the sense of permutation pattern. And this will require you to use a huge number of colors, but it will work. If we want to maintain the same number of colors, we can do that just by combining the color classes. So we can color an edge red if, for example, the delta sequence is red and monotone, or if the second element, delta 2, is bigger than the first and the third. And we can color blue if the delta sequence is blue and monotone, or if the second element is smaller than the first and the third. And then we sort of arbitrarily put in a color class for any other edge. And this is enough Because the main idea here is to find a long monotone delta subsequence. Because then we can repeat the same idea as before of using these properties of the delta sequence. Really, the only important part is that we have this ordering of the delta values, this strictly increasing or strictly decreasing ordering. And the proof that you can't have a monochromatic clique just follows through. So really the main idea here is to separate the two different types of monotone that you have and to have some amount of control over what sort of patterns you can find. And you can show that from these two properties, you can prove that the delta sequence must either have a unique local max or a unique local min. And because of that, you do get a long monotone subsequence just by taking one side of the local max or one side of the local min. And so you, in any of these cases, you will find a monotone subsequence in the delta sequence. Okay, so what were our ideas for stepping up? When looking at Ramsey numbers where we replaced monochromatic with spanning few colors, our ideas were to really analyze what's happening with the delta sequence, just forgetting about the context of colorings and Ramsey theory, and just looking at it in sort of a patterns and permutations sense. And what we showed was an Erdős-Hajnal type result. So if you're familiar with Erdős-Hajnal, the main idea is you have sort of a set of forbidden subgraphs, and you say a graph must either contain a large clique or large independent set, or it contains one of my special forbidden subgraphs. And we do the same thing for our delta sequences. Either we have a long monotone subsequence, or we have many of these forbidden subsequences. And we define forbidden as having this property LR. So this stands for the left-right property. And it's sort of a, I can talk a little bit more about it later. It's not super interesting to define this property right now. But the point is that this LR property is a pretty specific one. It's well defined. And we can actually count how many sequences or how many permutations there are with this LR property. So that gives us a pretty good handle on the maximum number of forbidden subsequences we could have with respect to this Erdős-Hajnal property. And so what we do is once we sort of have this result, then we use it to come up with a nice partition of the different patterns that our delta sequence can have. And the way we do that is we define our color classes based on, we sort of construct our color classes so that each class has at least one forbidden subsequence. So one thing that I didn't write here is that the strictly increasing subsequence we also define as its own class, and this you can see as sort of CP, as just the class of the strictly increasing or the strictly decreasing sequence permutation. And then for our coloring, we again sort of look at, okay, if our delta sequence is monotone, we color it one way. If our delta sequences are increasing, if it's decreasing, we color it a different way. And then if it's doing something else, then we put it in one of these classes based on what this permutation is. And using these properties of that we showed for the delta sequence, the proof follows through the same as in previous stepping up lemmas, where if we have a monochromatic clique under this new coloring chi prime, then you know, we show that in any of the cases, either we have some monotone subsequence or we have some forbidden subsequence, and containing the forbidden subsequence has implications for our delta sequence, which ultimately causes a monochromatic clique. So I'm sweeping a lot under the rug, but there's a lot of sort of technical details in there. But ultimately we can show this stepping up type lower bound for our Ramsey numbers, where you'll notice that I did have to increase the number of colors I'm using from Q to 2Q plus P, because there are 2Q colors contained in these two sets. So this is sort of the summary of our sort of new stepping up results. And there are some sort of observations that I wanted to make about these results. So remember that we wanted to show a tower of height log k as our lower bound. And I just showed you a stepping up lemma that if I applied it repeatedly, I wouldn't have a loss of a log factor. I would get a tower of height k. So what's going on here? Actually, there are restrictions on our parameters that prevent us from applying the result I just told you. And instead, we have to apply a weaker bound, where instead of stepping up from k to k+1 uniform, we step up from k to 2k uniform. And why is that? This is because of our restrictions on the value for p. So our value for p is at most the number of forbidden LR subsequences, forbidden permutations on K. And this number is exactly equal to CK, the kth Catalan number, because of course they have to show up everywhere. And so we can apply this lemma as long as our value for P, which is the number of colors that we require our cliques to span, is at most the kth Catalan number. But you might recall from the hedgehogs to cliques lemma much earlier that we required there P equals 2k plus 1, choose k plus 1. So recall in the hedgehog to clique lemma, we need P at least 2k plus 1, choose k plus 1. Because in that lemma, I said P equals 2k plus 1, choose k plus 1. Increasing that doesn't hurt us, decreasing it does. And so there is this very small gap. So if you remember your Catalan numbers, this is 1 over k plus 1 times 2k choose k, which is about 2 to the 2k. And so if we could even get an epsilon factor improvement in the exponent of this, we would immediately be able to apply this bound and stick it into this lemma, and everything would go through just fine. But somehow, and this is an exact result, so somehow we just sort of barely miss being able to chop off one of these log factors in our lower bound. And so what I mentioned earlier was like where improvements in this proof might happen. It probably would have to happen here because this is sort of an exact thing. It's an exact subsequence avoidance problem. Whereas here we just sort of came up with a nice, clever coloring of how to color a graph using hedgehogs. And it's possible you could come up with a different coloring that would reduce the requirements on this one parameter P. So it is sort of mildly annoying and more than a bit curious that we're barely just not able to apply a much better stepping up lemma to get the lower bounds on these Ramsey numbers. Okay, so that's mainly all I wanted to say about the specific sort of details of our ideas. But there are plenty of open questions that remain here. Another annoyance of what I just discussed is that we're not able to answer a question that Conlon, Fox, and Rödl posed in their hedgehogs paper if we just look at P equals 3. So what is this asking? This is asking if can we find a Q coloring of the 3 uniform clique on 2 doubly exponential vertices such that let's see, every KT spans at least 3 colors. KT3. So that's what this question is asking. And our methods don't apply here. We can't use the stepping up constructions, the colorings that we found, because of this annoying dependence on K, where P must be bounded by the kth Catalan number. Here, P is equal to 3, and the second Catalan number is equal to 2. So we sort of can't even answer the basic question that was posed here. And we can't even answer this weaker question of, you know, can we find some uniformity where for every P, there is some Q that could potentially be really huge, so that this Ramsey number is bounded below by some double exponential. So unfortunately, our methods don't apply here. But what we hope is that by just introducing this new notion of Ramsey number that hasn't really been studied a lot before, and by giving these new stepping up lemmas, that maybe this can provide some inspiration for other people to consider other bounds for this Ramsey number and maybe make some improvements to our methods that we use here. So I think I will finish there, but thank you so much for your time and thank you for listening.
Thank Corrine. And does anyone have any questions?
Can you maybe say a few more words about how the Catalan numbers made an appearance here? Kind of what's the core reason?
Yeah. So we our forbidden sort of subsequence property is what we call the left-right property, where we essentially say if you look at the unique, we look at sequences with, or let's say local maxima. If we take a local max here, then everything on the left is bigger than everything on the right in this permutation. And this we call it the left property. And similarly, we call, you know, the opposite, the right property. And so in counting these sequences, you can show that the number of these sequences is the Catalan numbers. But in terms of connecting these sequences to what's happening with the delta sequence, so with the delta sequence, a lot of the properties that are straightforward to prove have to do with local maxima and local minima. And so in particular, we were interested in exploring these so-called like maximum induced subsequences of the delta sequence, where maximum induced just means if you have your sequence elements, then for any 2 elements of the subsequence, everything else in the sequence between them lies below those 2 elements. And so we were able to show like Erdős-Hajnal type statements for these maximum induced subsequences, where either you have a long monotone subsequence or you have this particular type of maximum induced subsequence.
Okay, I think I get the sense. I have to say it's pretty crazy that the Catalan numbers almost match the upper bound you had for the hedgehog that you needed for the hedgehog graphs. I'm not sure I see why that would be the case.
I don't either. And we've talked to a lot of people who also don't understand why it is just so close. Because really, if we could tweak anything in either of the cases on the Catalan bound side or in the hedgehog to Kleek's lemma side, then it would just match up. But we really don't see any way to improve. Well, like the Catalan number is an exact result. So there's really no way to improve that end. So we're looking for ways to improve sort of the other end of the 2k plus 1 choose k plus 1 case. And we haven't found any so far. So we're not sure if it's an artifact or if it's really like you can't do better. Yeah.
There's definitely something going on there.
Yeah.
Something. Thanks.
Question. Is there any intuition on why the hedgehog graph is particularly important here and getting the gap, the polynomial and tower gap, and other graphs that might be considered besides that one?
So we haven't considered other families of graphs just because we sort of found this hedgehog and we're like, oh, this works. I think that in terms of why this particular type of construction works, somehow this this spine embedding is really important because in terms of the polynomial upper bounds, right? It's sort of very easy for this auxiliary culling to embed these spines. It's something that you can very easily get control over when you have these auxiliary colorings to find these hedgehogs. In terms of the tower lower bounds, I don't know that I have any good intuition as to why the Q color Ramsey number is necessarily so huge, because ultimately we just passed to cliques. So really the tower lower bound comes from proving things for cliques, and it just happened that for this cliques to hedgehogs lemma, there is a very easy way to color a graph with no monochromatic hedgehogs, just using a coloring with monochromatic cliques in it. So unfortunately, I don't know that I have any intuition as to why the tower lower bound is true for the Q colors. I think it would be interesting to see if there are other constructions that are very different from hedgehogs that would work for this.
Sort of piggybacking off of that, do you have any intuition for like what those gaps should look like for, I don't know, if you took like a random hypergraph of a particular size? Like,
that's a good question. I imagine that there are people who have thought about that, but I am not one of those people who have thought about what's happening with colorings of random hypergraphs. I imagine that people know that people like Jacob Fox and David Conlon know things about coloring random, or like the Ramsey behavior for like the clique and the K uniform case, but maybe this, like, if you relax the monochromatic condition to spanning few colors, that might not have been explored yet. But I also have no intuition as to whether Erdős's conjecture is correct. I mean, I have intuition and it goes sort of both ways as to whether these gaps are representative of what's happening in the original 3 uniform monochromatic clique case that we started off with. If like what the truth is there. So I think it's, yeah, I think that I have thoughts that are conflicting with each other. So I really don't know what my answer would be.
any other questions? If not, let's thank Corrine again. It's a great talk.
Thanks. Thank you so much for listening.